choice is that we have to understand what is this mass, what is this cross sections. So these are the may or may not be correct. If this turns out not to be the correct language to study the problem, then we may not go too far using this language to attack. But this is the language that we learn when we build the standard model, cross section, mass of a particle. So this is the thing that we feel more comfortable with. This is closer to our comfort zone as a physicist. So this is how we start from. And different scenarios will occupy different region of the parametric space. Say the WIMP, weakly netting massive particle, or the neutralino, which is related to the supersymmetry theory, is on this region, which is on the GeV scale, and then on this range of cross sections. And they are candidate with a much weaker cross sections. So this is the bring home message that most of the experimental efforts are somehow trying to explore scenarios, different regions of this parametric space. Okay, so we mentioned about this. One of the many theories that can put in energy contents to the universe without beyond a standard model is the supersymmetry theory. The supersymmetry theory is to have our standard model basically doubled. They have the standard model part have the super partners. So an electron will have a scalar electrons and so on. And this with this flavor to add, it will solve one. It may be able to solve some of the features of the standard model problems, like the hierarchy problem, and it may be help us to give an easier path to the brand unification. So right now, the standard model, our three forces, would not converge nicely at a high energy scale, but with supersymmetry, because among other things, because it has a lot of free parameters to tune at this point, is there are scenarios where they can nicely converge. But again, this is a theoretical speculations, and we would like to see whether LHC and so on would have hints of this. So now we discuss about the evidence of dark matter, and then propose that how we formulate the questions, and then the next transparencies would be on how the dark matter, on how to detect them as dark matter. So now, what do we don't know? We do not know what dark matter is, and we do not know what the new physics is. So this is question mark, this is question mark. But we try to attack the problem with the language that we use, that we have learned when we build up the standard model. So we start drawing something like, this is similar to a Feynman diagram. So now then we can ask the questions that if dark matter would intact and producing this standard model particle. So we want to know this, or we want to understand this. And there are different scenarios there. So to understand this block and this block, there are various ways, of course. So we can take out the thing that we love and then the standard model particle, collide them at high energy, and then to study whether they are new physics, and by studying their final state product. This is the approach of the production approach, as in the LHC accelerator. Alternatively, we can wait on Earth and ask the questions. And maybe in some high mass, high density, mass density region of the cosmos, they have enough mass that the dark matter tends to accumulate. And when they accumulate, they have a higher chance to interact among themselves. And when they interact among themselves, they may produce particles that we know and love, standard model particles. And we observe that on a satellite or on Earth. And then ask the questions: is it chance that they will come from the dark matter? So this is indirect detection. And then one more way is that we can have a standard model particle here as a form of a detector, and wait for the dark matter particle that really hits the solar system, hits that particular detector, and produces a signal. And then this is the direct detection mechanisms. Yeah. So for the indirect detections, we will jump over the accelerated approach for the reasons that it is more familiar to most people, as well as now the LHC is in full swing. They are trying to look for any anomalies in the LHC might have relevance to this problem. For indirect detection, we are asking the questions that when the dark matter accumulates in some region of the cosmos, they may impact and produce the things that we know and love: positron, electrons, neutrinos, antiprotons, and protons. And we try to compare them with what we think the background may be. And if there's excess, we have to be careful. Yeah. And then experimentalists look at the sun, look at Earth, kinetic center, halo, stars, and everywhere to look for scenarios like this. And among the various projects, I pick up a few that is on the news. So we have an enormous cosmic positron spectrum, starting from an earlier experiments of even heat, and then Pamela, and then recently the Fermi, and then AMS. The observation is as follows. So we can ask the question. We send satellites to space and ask, what is the positron energy? What is the positron distributions, momentum distributions in space? We have astrophysicists would tell us that we should expect a spectrum like this that falls, just like most astrophysical objects that will fall at energy. But the observations would tend to give a rise beyond 10 GeV. So we have an excess which is not understood by the current models of astrophysics background, both in positrons, and then there are two experiments. And so but the legitimate question is, there's an excess. It means something. There's a source that we don't understand. It doesn't mean that it has to be the dark matter or annihilations from WIMP. So the more work has to be needed. And among the new efforts are the AMS experiment, which this institute is a partner. The AMS experiment is a magnetic spectrometer that can differentiate positive and then negative charges. So it can differentiate positron from electron. It was put in the space shuttle in 2011, and last year it published results showing that the positron spectrum is consistent with earlier experiments, but with a more explicit and smaller error bar. So it supports the scenarios that we have a significant amount of a missing positron source. So there's a source of positron at this energy range, 10 to hundreds of GeV, and then we don't know what it is, but then how the subject would evolve is that of course it would be interesting to observe whether this would rise continuous or it would drop, and when it drops, what is the shape that it drops? That would tell us much about the nature of this source. And the AMS experiments is in a good position to tell us more, to give us more information as it collect more data in this region. Okay, and then besides observing positron, we can also look for gamma rays. Now, gamma rays, there are various detectors that can measure gamma rays from the sky, including the Fermi-led experiments. So the gamma ray, so one can look at the sky, the gamma ray sky. So what can one look at? So there are any anomalies we should be careful, and then would be a subject of research. And in particular, the smoking gun signature is that we can ask the questions that if you see the gamma ray is unlike positrons and electrons, they can come as a discrete energy. And then when they come discrete energy, you can scan the sky and see if there are spectral lines in some very strange, in some unexplained energy as a line, like 126 GeV, for instance. Then we have to be very careful that there's no standard model way to produce a resonance like that. Or we look for the sky in space. There are regions that do not have light, but it gives us an excess of gamma rays. Then we can also to be careful. But so far, there's no strong evidence on the gamma ray observations yet, except one, which is there are reports of an enormous 3.5 keV line. Just as a 3.5 keV is an X-ray line, a lot of atomic energies would produce that, and then some group of astronomers by putting different data together suggest results to have seen an excess at this region, and this aroused some interest, some risk. And of course, subjects like this, when we talk about keV, is an atomic physics. We have to understand the atoms well in order, not just atoms in the lab, but atoms over in the astrophysical environment. In order to be in control, that this is really from the dark matter decaying or from an X-ray source not yet observed. Okay, and we can also do this approach by studying neutrinos. So neutrinos, for instance, this is the famous Japanese super chemical experiments. It was built to study solar neutrinos and atmospheric neutrinos, and then also proton decay. But for dark matter, it can also make a contribution in the following. So a high energy muon neutrino will give us a ring like this. High energy electron neutrinos will give us a ring like this. Now these two rings are different. This is more fuzzy, and the neutral event would give us a ring like that, even more fuzzy, and then two loops. And to look for dark matter in this detector would be to look for enormous muon neutrinos from the sun, for instance. There are no known standard model way, nuclear physics way, of nuclear and particle physics way to produce high energy muon neutrino from the sun. If they would see this experiment would see in excess of this event, always pointing to the sun. Then this is a very strong Tsz-King signature that something is producing extra muon neutrinos. In this case, it would be the dark matter annihilating producing neutrinos. But so far, only upper limits are reported for surges like this. But conceptually, this is a very beautiful signature. And for WIMP directed detections, is to wait for the WIMPs to hit our detector. When the dark matter particle would hit a detector, it still carries some momentum. It will transfer the momentum to the detector. In particular, the more favorable scenario is that it transfers the momentum to the nucleus, and the nucleus moves. And when the nucleus moves, now then a lot of nuclear physics. When the nuclear moves, then of course a lot of nuclear physics comes in. So it will ionize the medium. It may produce heat, and it may produce light. So by observing the combination of ionization, of heat or light, then one can try to in a very low background environment, one can try to figure out what is the properties of its incoming source. So this is one scenario, and another scenario is that now this process, the dark matter comes, the Earth is rotating around around the sun, whereas the dark matter halo would be like this. So relative to the dark matter, there's a relative velocity difference between this nucleus and the dark matter halo, between summer and winter. One of the signature would be that we should be observing a change, a modulation of the rate, also energy spectrum between summer and winter, if the signature would be explained by an astrophysical halo object. So this is we look for nuclear recoil, and we look for annual modulations to establish the dark matter signature. Yes. Okay. Now among now we mentioned that there are different scenarios. We measure ionizations, photons, and heat. And obviously there are different experiments trying to do different combinations of this. Some experiments will try to measure both, and in such cases it can differentiate. It has stronger power to differentiate the electron recoil from a nuclear recoil, because you have two eyes. You try to measure the same phenomena with two different techniques. Then you have a stronger differentiation power. Whereas experiments some of the experiments prefer to do one aspect more sensitively, and then tries to explore other regions of the parameter space. So that's why there are various experiments trying to study essentially the same phenomena. And among the various experiments I mentioned that there's a Dharma experiments made up of sodium iodide, so crystal. So this is a substance that gives us light. And by measuring that modulation effect over a course of decade, 11 years, it reported some annual modulation effect. So within 1 year, it's weak, but within 11 years, it turns out to be a significant modulation effect. So an 8 sigma effect. Again, having annual modulation doesn't mean that it has to become from dark matter, but this is one of the enormous results which we need to worry about. Another technique is that a CDMS experiment would measure both heat as well as ionization. So by measuring both, we can differentiate between electron recoil or the gamma background, photon background from the nuclear recoil, which is more associated with dark matter. And then because of measured heat, it has to operate in very low temperature of millikelvin. Yeah. So now this experiment, for instance, in the last year, reported that we observed 3 events that satisfy all the criteria that it is related to a. This is in the center of the detector, not at the surface, and is consistent with the nuclear recoil. It's observed 3 events out of an expected background of this amount. So it is not compellingly high, but nevertheless it have an excess. So this is another enormous result with a probability of that it is just fluctuations to be that is over 5%. In that class of experiment is the xenon experiment. The xenon is a liquid noble gas. When you have a liquid noble gas, when the radiation or the dark matter comes, it will produce light. And it also ionize the medium. And if there's an electric field, if you want to pull the electrons apart and then goes to an upper region where charge multiplies, then it measures both the ionization as well as light. So both scintillation and ionizations. And therefore achieve different, and the size of these two signals will be different between nuclear recoil and electron recoil. So there are 2 experiments, at least 2, and then a third one is coming up. So the xenon series and the Lux series, they do the experiment and they both reported negative results. So they try to look for the effect, but the effect is not there. And for our laboratory, in this laboratory, that we are working closely with our colleagues in China in an underground laboratory in Sichuan, using a germanium detector. So germanium detector has a lower threshold than the other techniques, and then recently we are exploring the low end, the low mass range of the parameter space. So just now I mentioned that, for instance, the Dharma annual motion results, if it is explained by this scenario, would have an allow region here, and the CDMS result would have an allow region here. So for instance, this data set would be probing this region of the parameter space. Yeah. So a summary of the direct experiments is necessarily complicated because there are a lot of them. So now how to read this plot is that there are various allow region here in the low mass region from what we just now we mentioned about the Dharma experiment, the CDMS2 experiment data, and also from another experiment called Cogent. Whereas the various other experiments would plot exclusion plot, including the xenon and Lux and so on, they try to look for the effect and then you didn't see it. So there's already some tension, some conflict here. Shown here are some of the preferred parameter space from the supersymmetry for instance, and there's a lower bound. So in this search, at some point you'll be hitting some real background. And the background comes from what? Comes from neutrinos. The atmosphere gives us neutrino. The sun gives us neutrinos. So those neutrinos, when it hits the target, it can also produce nuclear recoil and the nuclear move, and then we will see the similar signal as a dark matter would. So this class of experiments would still have a few orders of magnitude to go, but eventually would be limited by, at this point, by the background from a neutrino process, which is interesting on its own way. Okay, so before I close my part of the presentations, I just highlight some of the things which Lin might elaborate further. So now I tell the stories about how to do the experiments, in particular in the direct detection experiments. So what, as an experimentalist, what are the things we have to worry about that is related to nuclear and atomic physics? Things are never so simple. For instance, quenching factor is ionization yield in nuclear recoil at low energy. So a nuclear recoil is a pick up the momentum, the nuclear move. But not all the energy is converted into ionization. So we need to know that ratio. And we need to know the ratio as lower and lower recoil energy. And sometimes in the presence of electric field and a magnetic field. So these are complications which we need calibration experiments on one hand, real measurement, as well as a theoretical guidance. That would be much of use. Channeling effect. In textbooks, we study ideal atoms, but in the real world, nothing is ideal. The atom exists in complex molecules, exists in crystals, maybe exists in semiconductors. These are the real stuff that gives us a detector. So, what is the difference between an atom and a semiconductors, for instance? So, are the quenching factor the same, exactly the same, or are the cross sections being the same? Are there modifications? And then, what would happen in the presence of an electric magnetic field? What would be the effect when we comes into the real world? Another nuclear atomic physics problem. Scintillation yield. Nuclear recoil, say in xenon, would ionize the xenon would be excited producing a spectrum. And the ionization energy is getting less and less. So how does the light emissions goes with the nuclear recoil energy? So this can be a subject of atomic physics. WIMP can also be an extended object, and we have to worry about the nuclear form factor in our detection. There are also research on WIMP, electron elastic interaction. So the WIMP, the most conventional way is to look for the nuclear recoil. But a particle can also interact with the electrons, and then the electrons can pick up the momentum and go. But in order to really study them, we need to know the realistic electron momentum distributions in an atom. So the electron is not stable. It's not at zero velocity in kinetic energy in an atom. So we have to worry about that. And last but not the least, we have to worry about at this point at low and low energy. We mentioned about the 3.5 keV X-ray line that can be a dark matter candidate. So we get into the atomic energy range. So so we can ionize. Atoms can be ionized as a ionization, as a detection channels. It can be due to the WIMP magnetic moment, to the WIMP charge, or from another class of a candidate called axion. They also have electromagnetic effects. So how do those cross section goes? What are the complications here and there? And then how would the atoms be ionized by a WIMP that may have magnetic moment or charge? So all this can be interesting subjects to investigate as a theoretical subjects as well. Okay, so I will pass the talk to Lin Xin, who would be more focusing on this aspects of the problem.
Yes, so thank you.
May I ask a quick question before that? So previously you mentioned some kind of limitation because of the background from neutrino. Does that only apply for the direct detection? How about the indirect search? Indirect search, you still have this.
Okay, now so this one is a cross section versus mass. So this plot is for the direct detection. So if you put a detector here, you have to worry about at some point neutrino from the sun, neutrino from the atmosphere. And for the indirect search, they have each class obviously have their own different background. So the neutrino coherent scattering background applies only for direct search. And but now since while we are on this subject, it is not insurmountable. Now you can imagine that if my detector have directional sensitivity, then I have better handle, because this neutrino comes from the sun, and I know where the sun is. So if there's a signal that comes from the sun, I know that this is from a neutrino. And if the signal comes not from the direction of the sun, then that would not be a neutrino. But these detectors still have to be invented. There's still a long way to build a detector with directional sensitivity, but with very low threshold. Yes?
It seems the background depends on the wind mass. How do I understand this?
The background now, so the general shape of this, how to understand this shape? Now this is the following.
I'm talking about background.
What
The neutrino.
no, this one.
Yeah.
So this one is from atmospheric neutrinos. This is a threshold beam. This is a solar neutrino. Because solar neutrinos is at most 20 MeV. So 20 MeV will only affect this region. whereas atmospheric neutrinos are higher in energy, it can be hundreds of MeV. So although, but it has less. So it affects a larger region of higher mass, but not. But then at low mass, we worry about the low energy solar neutrino. Okay. So, but after Nintina's presentation, we can have a more general discussions. Yeah. So shall we continue with the second talk?
Yeah.
Yeah. So.
So, thanks to the organizer for giving me the opportunity to deliver a talk here. So thanks to Professor Wang to give a very wonderful survey on dark matter and direct dark matter detection. So here, I will focus on these few nuclear and atomic physics items related to this direct detection experiments. And there's a two common category that is from the detector response models, include the quenching factors, channeling effect, and nuclear form factors, as well as this detection part, which I pick up some interest topic related to us, which is the WIMP electron interactions and some detection channels beyond this standard, which we call standard detection related to this spin dependent and independence. So this the standard dark matter detections, and here is the detection rate from the detectors, and this exposures, and here is the form factors, and this one as the cross-section, and and plus this strong physics models related to these velocity distributions and scale velocities and the density dark matter in local Earth. So, what is the relationship between this simple formulas and relative to this atomic and nuclear physics? So from this detector response models, we can talk about this channeling effect and quenching factors, as well as this QED at the low energy of the KEV, which is the atomic physics regions. And meanwhile, there's cross-section actually from the particle physics that is writing this dark matter have the covering with this proton and neutron, and actually it contains this quark contents in nucleon. And also there's detection channel, which relative to this topic is WIMP electron scattering, or the axion-like particle dark matter or hidden photons, which involves the detection channels, something like these atomic ionizations or the new detection channels that did not be observed. So we will come to this quenching factor problem first. So what we observe from the WIMP is the nuclear recoil from the detector. And unfortunately, there's not the energy that we detect by the ionization detectors or scintillating detectors. And due to the energy sharing lost by the heats. And this one actually for experimental fact that